Hello, I am Andrew Cirincione, and this is my project on fractals for Math 692. Let's get started. So we'll start off with what are fractals? Fractals are complex geometric shapes that hold structure over infinitesimally small scales. A very good simple example of this is the Sierpinski triangle that we see on the right. For example, you could take the bottom third triangle, and if you were to expand that to the size of the original triangle, it will be the exact same set. And this is because, or the exact same fractal, because this is a self-similar fractal, which means that it maintains the same pattern no matter how arbitrarily close you may examine it. Fractals were not understood until Mandelbrot in 1980. It's debated as to whether he was the first one to discover them, but he was definitely the first one to do a significant amount of research into them. So, to understand fractals, we will start with a basic concept of different types of infinity. So, your intuition might say that there's only one type of infinity, because how could infinity be different from another infinity? This is an example that you probably encounter a lot that you don't really think about in terms of countable and uncountable infinities, which are actually two distinct infinities, with uncountable being larger. So if we look at the countable example, the natural numbers, it's very easy to conceive of. 1, 2, 3, 4. If I were to ask you what comes after 4, you'd say 5. If I say any natural number, you can tell me the next element in the set of natural numbers. However, if we go to the uncountable infinity and we reference the real numbers, and we just say, okay, let's go from 0 to 1 in the real number scale, and say the next element in the real numbers after 0. You'll notice that this is impossible. You cannot say the first real number after 0 because it is infinitesimally small and impossible to determine. So these are the distinct two types of infinities, and these will help us understand fractals as we move forward. So, some more examples of countable infinity. A set is countably infinite if it can be paired with, if each element can be paired with a natural number. For example, positive and negative integers are very easy to do this with. So you may say, okay, we want to start with the integer 0. You compare the integer 0 with the natural number 1, and then we have negative and positive 1, the integers that we want to pair. So we compare positive 1 with the natural number 2, negative 1 to 3, and then we're concerned about 2 and negative 2. We can assign 2 to 4 and negative 2 to 5, and so on. You might be wondering, okay, so it seems like the count for natural numbers is increasing far greater than we're counting up integers. But it doesn't matter, because keep in mind that we're working with an infinite set. The natural numbers are infinite, so you can always pick another natural number to assign to an integer. Thus, the integers are countable. Using the rational numbers is also a pretty unique case that I like, because so if we just look at the rational numbers, we know that they're constructed as p over q, where p and q are integer values. We're just doing this for the positive rational numbers, but this can be done with the negative rational numbers as well, or just all rational numbers. And the way we can tell that the rational numbers are countable is we can set up a matrix-like style for representing all of the rational numbers, where the row of the matrix corresponds to the numerator and the column of the matrix corresponds to the denominator. So with that in mind, you can designate, or you can find any rational number. If you were to say, okay, where is the rational number 100 over 30? It would be very easy to find. You'd go down 100 rows and you'd go across 30 columns, and there would be the number that you're looking for. And thus, since we can always assign these rational numbers to some coordinates corresponding with the natural numbers, they are countably infinite. So now we may move on to uncountable infinity, and we are going to prove why the real numbers are uncountable. It might be obvious that they're uncountable from my example earlier, seeing that you cannot name the first element after 0, but we will do a proof here. So it's going to be a proof by contradiction, so we are going to begin by assuming that we can write out each real number x sub n in a set from x sub 1, x sub 2, x sub 3, all the way up to x sub infinity. So x sub 1, we know that each element, since it's a real number, I believe I failed to mention that these are also just the real numbers between 0 and 1. This can work, this method can work for other real numbers, but we're just using the between 0 and 1 as a just as a smaller example, but it will apply to all real numbers. So we know if we have these x sub 1, x sub 2, and x sub 3, and so forth in our set of real numbers between 0 and 1, we know that they are going to have some elements in their decimal places. So such as take x sub 1 that we see in its first decimal place is x sub 1, 1. In the second decimal place is x sub 1, 2, and in the third x sub 1, 3, and this is the same respective for all the elements that we're considering in the set. So what we're going to notice is if we take the first decimal place, the element in the first decimal place of x sub 1, let's just take that down, refer to my example with the arrow. We take the 3 in the first decimal place of x sub 1, and then we can go down the diagonal. So we could say, okay, take the 9 in the second place of x sub 2, take the 2 in the second place, in the third place of x sub 3, and do this for all infinite elements in the set that we've constructed. So if we select all those diagonal elements and then assign them to a new number, here we call it r, and say, okay, so what we were looking at down the diagonal, we were looking at 3 as the first decimal of x sub 1, 9 as the second decimal of x sub 2. So let's say we have r equal to 0.3 prime, 9 prime, 2 prime, where the prime of the diagonal elements is just any number that is not that diagonal element. So here, for example, our r could be equal to 0.157, continuing, because 1 is not equal to 3, 5 is not equal to 9, and 7 is not equal to 2. You could choose any number that isn't that aren't those numbers, 3, 9, and 2, but this is just an arbitrary example. So what that tells us is that, okay, we've constructed an element that is definitionally different from every single element in the infinite set of elements that we assumed the reals could fit in, the countably infinite set of elements that we've assumed the reals could fit in. So since we've shown that there is an element that can be constructed out of the existing infinite elements in the set that we've defined, we have shown that not all elements are being accounted for in the real numbers, because we can say, okay, we came up with this countably infinite set, but it's not accounted for this arbitrary r that we have just designed based on the infinite elements inside the set. Thus, since we assumed it was the reals between 0 and 1 could be placed in a countably infinite set, and we have shown that there are elements that are not being accounted for, we have proved that the real numbers are uncountably infinite. So with that, we can move on to our first fractal. It's a very simple fractal, which is the Cantor set. The Cantor set is very easy to understand. You just take the first element, you take the left third and the right third, and you bring them down for the next element, and you delete the middle third. So we can see that clearly from S1 to S2. We are taking the left and right third and bringing them down. And then for S2 to S3, we're doing that respective action to both the two intervals that we have in S sub 2. It's pretty easy to imagine that pattern, and as we go to S sub infinity, that is the Cantor set. So there are three specific properties that the Cantor set has. It has structure at small scales, which means that we can continue to examine this Cantor set at arbitrarily small, or we can zoom in arbitrarily much, and we are always going to see this structure. And the thing with the Cantor set is it's also self-similar. So in addition to seeing structure at arbitrarily small scales, we will also see the same exact structure throughout. And number 3 might be a little hard to understand now, but we will approach it later, which is the dimension of C is not an integer. And this is the same dimension that you would be thinking of with like a line is one-dimensional, a square is two-dimensional, and a cube is three-dimensional, and so on. The thing about fractals is they're not necessarily integer dimensions like that, but we'll approach that later. So, using our knowledge of countable and uncountable infinity, let's see if the Cantor set is countable. So, it's what we can do. It's very easy to assign numbers to each point in the Cantor set. So, in general, we can say that, okay, if a decimal place is a 0, that means we are talking about the left partition of that line. If it is a 1, we're talking about the middle third partition. And if it is a 2, we are talking about the right third partition of that line. So as we can see, in S sub 1, 0.0, as we have 0 in the first decimal place, means that we are dealing with the first, we are dealing with S sub 1, and we are looking at the left third. And it's the same for 0.1 and 0.2. If we're looking at 0.2, we're looking at the right third of S sub 1. So then if we continue, for example, let's say we went 0.21, we know that we're dealing with, okay, 0.2, that is in the first decimal place. So we move to the right third, and then we have 0.21. So we are going to the original right third, we're going down, and then we're going to the middle third of S sub 3. Oh, I'm sorry, that should be S sub 2. That is labeled incorrectly. Moving on. The logic still applies, though, of the coordinates that are being denoted by the 0.21 and stuff. 2, you go to the right third. 1, you go to the middle third in the next iteration. The Cantor set continued. So we can now show through through constructing the points in the Cantor set as such, as we just did, we can show that the Cantor set is actually uncountable in a very similar way that we showed the reals are uncountable. So if we were to say, all right, let's design a countably infinite set with C1, C2, C3, to C whatever, that will contain all of the points that we want to reference in the Cantor set. So what we can do there is we can do what we did very similar to the real numbers, and we can take the diagonal of the the first decimal place of C1, the second decimal place of C2, third decimal place of C3, and so on. And we can take any number that is not those decimal places and call that C prime, and just set it equal to all the numbers that are not the diagonals of C1, C2, C3, and so on when you write that out. So as we just did for the real numbers, we have constructed a number that is not represented in the original countably infinite set, and thus the countably infinite set does not contain all of the Cantor set points, so the Cantor set is uncountably infinite. Now, I was talking about this before when we were talking about the Cantor set not having an integer dimension, and we will explain why that is now. So what is dimension? It's very important to define it before we start questioning why fractals don't really work with it. So It's very obvious that lines and smooth curves are one-dimensional, planes are two-dimensional, cubes are three-dimensional. That's very whatever. That's obvious. So we could use a definition for dimension that the dimension is the minimum number of coordinates needed to describe every point in the set. So we can clearly apply this to a line. If we're just thinking about like the x-axis as a line, you only need one number on the to know where you are going to be on the x-axis. If you say 5, all right, we're at 5 on the x-axis. That's simple. If we're working in 2 dimensions, it's clear that okay, think of that like in an xy plane. If you give 2 numbers, you can tell anywhere you are on that xy plane. The thing about this is that doesn't really work for fractals. So we'll see how using this seemingly trivial definition of dimension is actually going to kind of fall apart when we're looking at fractals. So the first thing that we can look at that displays this property is the von Koch curve. So I'll just walk you through how it's constructed. If we look at S0, you can see there we just begin with a straight line. S sub 1 is taking that straight line, it's shrinking it down 1/3 and creating 4 copies of it. The triangle in the middle is formed out of 2 copies of S sub 0 scaled down by 3. So we see I wonder if you can see my mouse. Oh yeah, you can see my mouse. Okay, that will make this easier. So this section right here is 1/3 of S naught. This section right here is also 1/3, 1/3, and 1/3. So there's 4 copies scaled down 1/3 from the original. So now if we do this pattern again, so we take S sub 1, we scale it down 1/3, and put it on and copy it 4 times, we get S sub 2. And note that these elements at an angle are just S sub 1 at about a 45-degree angle. And we just continue to do that for S sub 3, S sub 4, to infinity. And there's something important to understand about this is, okay, so as all these curves get increasingly complex and increasingly dense, they're going to get infinitely dense to the point where if you start anywhere on the curve, if you point to any point on the curve as the curve goes on for infinite iterations, you cannot get to anywhere else on the curve at all, because you have to go through an infinite complexity of curves that have been generated through this pattern. So that being said, the length between any 2 positions is infinite. So the von Koch curve is clearly not 2-dimensional because it does not have any area, but it's also not 1-dimensional because it has infinite length between any 2 points on it. So how can we find the dimension of the von Koch curve? We can start with something more simple. So we can look at the left square that's split into 4. So if we take, let's assume that the original square is not separated into 4. We can take that original square, if we scale it down by 2, and then fill up the squares, fill up the original square with the square scaled down by 2, we can fit 4 squares in there now. So that our scale factor would be 2, which would be set equal to r, and our number of copies is 4. So that is set equal to m. So we can clearly notice the relationship here that m, the number of copies, is equal to r, the scale factor, squared. Note that this is squared because we're going to see that this corresponds to the dimension that we're working in. As we're working with a square right now, we're clearly working in 2 dimensions. So now we can look at the middle example. If we scale the original square down 3, we can fit 9 copies of that scaled down square inside of the original square. So m is equal to 9 as there's 9 copies. R is equal to 3 as it's scaled down by 3. So 9 is equal to 3 squared, clearly, and we're still working in 2 dimensions, so we're squaring. Now, if we look at the cube on the right, if we scale down the cube by 2, we can fit 8 scaled down cubes inside of the original cube. 8 scaled down cubes scaled down by 2. So if we now look at the relationship between m and r, we can see that 8, the number of copies, is equal to 2, the scale factor, cubed. And this directly correlates with the fact that we are now working in 3 dimensions, hence m is now equal to r cubed. So we can get a general rule out of that m is equal to r to the power of d, where d is the dimension of the object that we're observing. So if we take that and solve for d, we can see that d equals the natural log of m over the natural log of r. Continuing on, we can apply this to find the dimension of the Cantor set. Remember, I said before that it's not going to be an integer, so let's see what it will work out to. So we want to find the scale factor, of course, so we can see that the previous element, s sub 1, is scaled down by a factor of 3 and then copied twice for s sub 2. So our scale factor r is 3, and our number of copies is 2. So d is equal to the natural log of 2 over the natural log of 3. That's just plugging into the formula we got before, and that's about 0.63. So the Cantor set is about 0.63 dimensional. If we now apply it to the von Koch curve, we can see that, okay, as I pointed out last time, the way it's constructed, it is scaled down by a factor of 3 and copied 4 times, 2 times at an angle in the middle, and then that is repeated, so on and so forth. So we can see scale factor is 3, number of copies is 4, so d is equal to the natural log of 4 over the natural log of 3, which is 1.26. So the von Koch curve is 1.26 dimensional. Now, the strategy that we were just using, m equals r to the power of d, only works for self-similar objects, self-similar fractals. So we were just looking at the von Koch curve. Obviously, if you keep zooming in on it, it's going to maintain the same pattern and scaling throughout, and as does the Cantor set. But in order to do this for non-self-similar fractals, we need a new technique, and we can call this technique box dimension. I will point out right away that there is an error on this slide. This should be d is equal to the limit as epsilon goes to 0, not to infinity. But let's walk through this slide and explain it step by step, because the box dimension is slightly more complicated of a method. So if we let n of epsilon be the minimum number of d-dimensional cubes of side epsilon needed to cover our object, we can continue with that and look at the 2 figures provided on the left. If you need to pause the video and reread that sentence, that is totally fine, because I needed to take a while to understand this. So, as we can see in figure 11.4.1 from Strogatz's book, that n of e is directly proportional to the length of the curve over epsilon. Notice that the power of epsilon is just 1, because we are working with a one-dimensional object. It is a bit misleading that they are still drawn as, on the left example, as squares, because the box dimension rule, or the box dimension method, states that we're working with d-dimensional boxes, and the thing is that a one-dimensional box is just a line. So I think that could be expressed better in the book. However, I hope that helps you to understand what we're actually looking at. So it'd pretty much be saying for that left figure, the line, it's pretty much saying that, okay, n of epsilon is the number of one-dimensional boxes you would need, one-dimensional boxes of side epsilon you would need to cover the object. As we decrease epsilon, we're going to notice that that n corresponds to the power rule 1 over epsilon to the power of d, where d is the dimension of our object. If we look at the second figure, in figure 11.4.1, we could see that we're now working in 2 dimensions. So n of epsilon is directly proportional to the area over epsilon squared. Now we could see that that the boxes are actually squares here. They're 2-dimensional squares, and they're used to cover the area of the shape in question. And as we make epsilon smaller, it's going to be a more exact covering of the shape in question. This method is a lot like using a Riemann sum to calculate the area under a curve as opposed to an integration method. And obviously for a Riemann sum, you want to make the rectangles you're using to approximate the area as small as possible to get the best possible approximation. This is a very, very similar idea to that. So what we get out of that is, like I said before, we see the power rule develops of n of epsilon, the number of intervals you need to cover the object, is directly proportional to 1 over epsilon, the length of the d-dimensional box, to the power of d. So if we solve for d, we get d equals the limit as epsilon goes to 0. That is a typo. It should not be infinity. The natural log of n of epsilon over the natural log of 1 over epsilon. So moving on, we can use this for the Cantor set again, and we could just check that, okay, let's see if this corresponds to the previous rule that we developed. This box dimension method is a lot easier to understand once we look at a practical application of it. So we can see that S sub 0 is clearly one interval of length 1. We'll just say that is length 1, and it is clearly one interval. When we move on to S sub 1, we see 2 intervals. That's the left and right thirds of the previous entry. We can see 2 intervals, and they're clearly 1/3 the length of the original, because that is how we defined it. It's the left and right thirds that we're picking. So S sub 2 then is 4 intervals of length 1/9, and so on. So what we can say there is that the relationship between our n of epsilon and epsilon is that when n of epsilon is 2 to the nth power, we're going to need intervals of size 1/3 to the nth power. So if we plug that into the equation that we found before, we see that we can take the power n outside of the natural log, and we can cancel it out, so we get the natural log of 2 over the natural log of 3, which is about 0.63, which is exactly what we got before. But that was a self-similar set. So we want to try this box dimension method out on a non-self-similar set. So I'll walk you through how this one is constructed. So for S sub 1, a square is split into 9 equal sections, 9 equal squares, and 1 square at random is deleted. In S sub 1, it is the left middle square, but it could be any of them. And then in the next iteration of the fractal, the 9 cubes, or the 9 squares that the previous square was divided into are divided respectively into 9 squares themselves. And then one of those 9 squares for each of the last 9 squares is going to be deleted at random. So if we just want to walk through, so this square right here, these 9 squares corresponds to this square over here. So this square was split into 9 parts right here, and 1 square in those 9 squares is selected at random to delete. This goes for this square as well, and we are not concerned about the square in the left middle because that was deleted previously. So if we just want to look at, if we just want to count the number of intervals that we're using and how many intervals we need of length epsilon and so on, and how that applies to this, it's actually very easy. So we could see that there are 8 squares in S sub 1. It's not 9 because we deleted 1. And as this is split into 9 squares, we can see each of those squares, each of those 8 squares, has side 1/3 of the original square. So if we move to S sub 2, we can see that that has 8 squared squares, or 64, and these squares are all going to be of side 1/3 squared, which is 1/9. And that is clear, as you can see, that the if we just look at the bottom row, there are 9 squares. So each one of those squares is going to have the relative length 1/9 of the original. So we can generalize that pretty easy. We could just say, okay, so n of epsilon, or just n as I have it written here, when it is equal to 8 to the power of n, the size of the intervals that we'll need, the intervals being, the number of intervals being 8 to the power of n, the size of the intervals will be 1/3 to the nth power. So we can plug that back into the equation that we got before. Once again, this is a typo here. This should be the limit as epsilon goes to 0. So we plug in 8 to the nth power, 3 to the nth power, and we see that the n's cancel out, so we get the natural log of 8 over the natural log of 3, which is about 1.89. I'm not going to spend too much time on this slide because I don't think it's that interesting, and we haven't, in this class, covered too much on chaos. So I'm just going to run through it very quick. It's a lot like the box dimension method, except we're using a circle this time. So if we're doing this to approximate the dimension of a strange attractor, some strange attractor A, we just choose some point x on the strange attractor A, and we say, okay, so let's make a circle of radius epsilon around the point x that we just chose, and n sub x of epsilon is the number of points contained in that circle of radius epsilon around the center x that we chose. So we get the rule, the power rule of n sub x of epsilon is directly proportional to epsilon to the power of d, the dimension, as epsilon increases. So the book that we're working with, the Nonlinear Dynamics and Chaos by Stephen Strogatz, doesn't really go through the calculations used here. It kind of just jumps to the fact that, okay, so the overall dimension of A is found by taking the average n sub x of epsilon value over many x, that being just the arbitrary x's that we choose on the strange attractor A. We average that together. We average the n sub x of epsilon together to get the quantity c of epsilon, which is directly proportional to epsilon to the power of d. And d here is referred to the correlation dimension, but for all intents and purposes, we're just going to consider it the dimension. So when we graph the log of c of epsilon, which is the average of n sub x of epsilon over many x's that we chose, against the log of epsilon, we see that we get the figure in the bottom left, figure 11.5.2. You'll notice this curve has almost kind of an S shape. So, but we were only concerned with the scaling region, the region that we can observe has a constant slope. We are not concerned with the value of log of epsilon after or before that, because if you just think about it practically, if we are observing some point x and we have a circle of radius epsilon around that x, and we're concerned with how many points are going to be in that circle, if epsilon is very, very small, there's really only going to be that point x inside of the circle. And as we expand epsilon, more and more points on the attractor will be accounted for. That is when we get the scaling region with the constant slope. And as we make epsilon bigger and bigger, we get oversaturated with points, and then the use of epsilon bigger than that becomes obsolete. So we get our constant slope, and we call that d, which is the dimension of this strange attractor in question. Now we will move on to the really cool stuff, or the stuff that I think is really cool about fractals. And this is coming back to Mandelbrot's initial study of fractals. So, and they can actually be used to generate art, of which I will be showing you at the very end. So, the Mandelbrot set, which is a fractal, is generated by a very simple iterative method. It's simply, okay, so x sub n plus 1, the next x in our iteration, is determined by the previous x sub n squared, plus a constant c. So using that iterative method, the Mandelbrot set is defined as the set consisting of all of those complex c values, so complex constants that we plug into c, for which the corresponding orbit of x naught equals 0, the initial condition in the iteration just equaling 0 for x naught, under x sub n squared plus c, which is the iterative method, does not escape to infinity. So just as an example, I can't promise it'll be correct. Let's say we had like 1 plus 0.2i that we plugged in for c. If we ran the iteration over and over again, we found, so we'd have x naught squared, 0 squared, plus whatever I said, 1 plus 0.3i. If we keep doing that and we see that the iterative method never just escapes to infinity, it doesn't start going like, oh, okay, 1,000, 1 million, 1 trillion, then that is not inside the Mandelbrot set. We want something that is going to converge. So a popular way of visualizing the Mandelbrot set is graphing it on an xy plane, where the complex coefficient c is determined by the xy coordinates. So we could just set up any xy plane. It is also normalized, I believe, from 0 to 1 for both x and y, but I might be wrong on that. It's some small normalization region that we're working with, because when you start plugging in like 5 plus 10i, it's just going to escape to infinity. So I believe it is normalized around 1. So it's important to keep that in mind, that we're really only dealing with complex values with real and imaginary components that are around 0 and 1. So we use that xy plane that's going from 0 to 1, maybe. I kind of forget. We use that to construct our complex value c, where the x coordinate, wherever we are for the x value on our graph, that is going to be the real component of c, and then y is going to be treated as the imaginary component of c. So at each xy coordinate, the iteration is run a certain amount of times that is determined beforehand by whoever's coding it. So the iterations are run, and the whatever you're using to code it will determine, okay, so in this many iterations, was it converging or was it escaping to infinity? If that respective c value, that xy coordinate, causes the iterative method to converge, in the upcoming figure we're going to see that is treated as black, and if it escapes to infinity, it will be colored with some color. So we can see that when we do this, when we use the xy coordinate to determine c, we get this image, which may or may not seem familiar to you. This is a visual representation of the Mandelbrot set. And the code is actually extremely simple to generate this. If we look at the bottom, it's just for x in range, for y in range. That's simply just running through, the entire, all of the xy coordinates on the graph. It says, okay, so take each xy coordinate, plug it into our Mandelbrot function, which is Mandelbrot of x and y, and set our c, our constant c, equal to a complex number with a real coefficient equal to x, and an imaginary coefficient, the imaginary coefficient equal to y. And of course, x naught is 0, as that is the orbit we're concerned with for the Mandelbrot set. This is for I in range 1 to 1,000. That is the amount of iterations we run through. to see whether or not the given C value, the C value determined by x and y, will converge or diverge. You can increase this however much you want, and you will get a more accurate outcome. However, it's also more computationally intensive, obviously. And the way the code determines in the loop if the iteration is escaping to infinity, it simply says, okay, so if the absolute value of C becomes greater than 2, then we are diverging. So we will assign it some color. But if we take the Mandelbrot set and tweak it slightly, we can get Julia sets. So before we were getting the coefficient C, we were determining C from the xy coordinates on the graph. However, if we then just set C constant prior to our whole simulation, so C is not going to be dependent at all on the x and y coordinates of the graph of the simulation, and just say, okay, let's set C equal to something like, I'll use the same example as before, 1 plus 0.3i, and instead we we replace x naught equals 0 with x naught equals a complex number determined by that position on the xy plane, where x is the real component and y is the imaginary component. And so it's really pretty much the same idea, except x naught is being changed to what we previously had determining C for the Mandelbrot set, and our new C is just some complex number that we decide before running the simulation. There are plenty of different constant C's that you can use to get a lot of different cool imagery, and that's what I will be showing you on the next slide. So everything here I am showing you is figures that I've generated in Python myself. So we have this one right here, and we also have, here's some cool stuff I made. We have all of these fractals that I generated using the Julia set, and just the only difference for pretty much all of these, not accounting for the change in color, which is I pre-designed the color beforehand, but the entire process is exactly the same for developing all of these. The only difference is the constant C value that we choose. It would be somewhere around like 0.17 plus like 0.08i would get you a completely unique pattern, and you could just come up with you could just plug in whatever you want and see if it comes up with a cool pattern. There are some online tools that can give you constant C values that will always give you some really cool pattern, and I highly recommend looking into that because there's some really interesting stuff on that. And also, if you are interested in any of this, I would highly recommend looking up Mandelbrot zooms on YouTube, because the thing is, the Mandelbrot set is a fractal, so it has complex structure at arbitrarily small scales. So you can keep zooming into the Mandelbrot set, and you could also keep zooming into these Julia sets, and you will see an infinite complexity of changing, maybe some repeating patterns. The Mandelbrot set is not completely self-similar, but you can find the Mandelbrot set inside of the Mandelbrot set. So that is all I have for explaining fractals, and I hope this piqued your interest on the topic, and thank you for listening.